two graph models, simple graph and attributed graph, but we have focused on traditional algorithms on the graphs, shortest path, various cycles, minimum spanning tree, and other things. Now we are going to look at aggregate analysis. Now aggregate analysis is somewhat different from the algorithms that we have seen or algorithms that we wanted to use in the graph earlier. What aggregate analysis means, you are trying to get a broader understanding of what is in a graph, a more general and global understanding of what is in a graph, and this is done using various concepts such as the notion of a community, the notion of a hub or centrality, and the notion of a substructure. There are also motifs and various other things we will not have time to go into. So, just to give an understanding of the complexity involved in various things, enumerating all the substructures of a graph has exponential complexity. So if you want to systematically enumerate all subgraphs from a given graph, so suppose say you have a graph of 50,000 nodes and 100,000 edges. Now you have to enumerate graphs of size 1, that is one edge, graphs of size 2, subgraphs of size 2, all subgraphs of size 2, all subgraphs of size 3, that's an exponential problem. So the number of such is 8. So this is very computationally intensive. Subgraph isomorphism that we will see is also NP-complete. Remember I talked about two graphs, bipartite graphs, they are isomorphic. To finding whether this graph is isomorphic to this one is NP-complete. However, they say it's difference between subgraph isomorphism and graph isomorphism. This belongs to a different category. The other thing is there is something called the notion of canonical labels. So you can order a graph using the notion of canonical labels, and that computation is factorial. Factorial is really bad. Factorial is worse than exponential, where V is the number of vertices. All approaches have to deal with the above in order to be able to work on large data sets. Different approaches do it differently. Scalability depends on the approach and the use of representation. So this is very important to understand. So we just talk about scalability, but achieving scalability is not easy. So let us look at community. So what is a community? Remember I talked about a clique, and then I said community is an approximation of a clique. So we are going to detect communities in a very large graph. So some real life examples of where community is useful from an analysis perspective. Groups of people who are friends on Facebook. So if you want to find all the people or different groups that are friends on Facebook, it is not that everyone is a friend of everyone, right? There will be cliques. This set of people are friends together, another set of people are friends, another set of people are friends. So if you take the Facebook graph, which is very large, remember, number of nodes are in millions. Edges are also very large because of the friendship. Now you have to detect communities. Which group? This group, how many nodes it has? How many edges it has? This community, how many? Because the interaction between these communities is very less. There are very few friend relations between this community and this community. But this community is very strong, this community is very strong. The same thing is true on LinkedIn. So certainly it is possible for me to take a Facebook graph and find communities. I can also find connectedness for LinkedIn graph, but if I want to find together what are the communities across Facebook and LinkedIn? That is not easy. That's what this one is saying. Groups of people who are friends on Facebook and connections on LinkedIn. How do you find that? So we will see this tomorrow using the notion of multi-layer network, how this can be accomplished. Groups of researchers who have collaborated on research papers. Again, not every researcher collaborates with everyone else, right? There are communities. So these set of people work together, these set of people work together, these set of people work together. How do you find them across all the researchers, not within an institution? You can also do it within an institution if you want. Groups of proteins with similar functionality inside a biological cell. This is from the biological domain. This is also important. Accident-prone regions based on poor light conditions are bad with. So we have done some works in what we call disaster graphs. So we have data set from UK accident. So UK has a huge data set for each year where they have listed every accident for that year. Location of the accident, latitude, longitude, road condition, weather condition, whether it was snowing, it was not snowing, whether it was raining, whether it was sunshine, whether it was a fatal accident, whether it was a non-fatal accident. So you may ask, why is this important or why is this useful? So if you have this kind of data, they want to know what are the regions where a lot of accidents are happening. How do you find that out? How do you find out the regions where there is a concentration of accidents, maybe due to a particular weather condition? Due to rain, this particular region has a lot of accident. Due to snow, this particular region has a lot of accident. This is useful because they have to take remedial or preventive measures. And if you have a limited amount of budget, then they have to decide where to spend it. Okay, so these are the real world questions that needs to be answered by the analysis. So I'll show you, when I show you the dashboard, I'll show you some examples of how we have done that. In general, group of entities who share common properties and or play similar roles need to be detected as a community. So let's take an example to make things clearer. Suppose say you have this graph. This is by no means a very large graph. We can visualize it, we can see it, we can understand. So the question is, what are the communities in this graph? Are there communities in this graph? Is there one community or multiple communities? And why do we say this community is different from different community? So that is the question. Groups of tightly connected vertices in a graph. So you can sort of estimate. You can see that here is a group of nodes that are tightly connected. Here is a group of nodes that are tightly connected. Here is a group of nodes that are tightly connected. Here is a group of nodes. But across these, there is connectivity, but very small. So from this, you can, so they are not clicks by no means. This is not a click, this is not a click, this is not a click, this is not a click. Groups of related nodes densely interconnected and have fewer connections with the rest of the network. So in this one, you can identify 4 communities. Green is a community, blue is a community, yellow is a community, red is a community. So we can see this in this graph, but if you are given a graph of 500,000 nodes and 2 million edges, how will you compute it? That is the challenge. Developing an algorithm, developing an efficient algorithm. That is the challenge of analysis. Analysts may just applying the package without even understanding what it does. But development of some of these algorithms is not straightforward. They are very complex algorithms. They are NP-complete problems, so computationally very expensive. You have to use heuristics, you have to use dynamic programming, branch and bound, lot of different techniques to do that. So now, do you see what is the difference between a clique and a community? Why these four can be identified as communities in this larger graph? So given this graph, can we spit out these four communities as communities whose property is they are densely interconnected. Each of them is densely interconnected, but fewer connections with the rest of the network. That is what is important. Questions? So here are some other examples of communities in very large graphs. So these look like blurs because the graph sizes are, this is an internet. This has millions of nodes and edges, but still you can see communities with different colors. This is a football network. So in the US, football is a big thing, and you can see, in this one you can clearly see there are net communities here, there are sparse connections between there, so there are different communities. This is a power grid network. So you have communities or regions when there is a big city. Here is a books network. Again, you can see communities in different colors. So communities are very important from an analysis perspective. And computationally, it's expensive. So what are the different types of communities? One is what is considered a flat community. These are communities that are disjoint. These are non-overlapping communities. So that means there is no node shared between the communities. You can also have hierarchical communities. You know, if you have done mining, you will see that these 6 communities can be hierarchically grouped into different hierarchies. So you can group these two into one hierarchy, these two into another hierarchy. This stands out separately. So you can have hierarchical complete communities. Now there are different ways of doing it. You know, if you have taken a mining course, you will know single linkage, complete linkage. There are various ways of clustering, and you can further hierarchically combine these things further. So there is hierarchical clustering that can also be applied to this one. You can also have overlapping communities. For example, these are overlapping communities where nodes, some nodes are in both the communities, in this community. So when you develop algorithms, this becomes a parameter. You can say, I want only communities that are not overlapping, or I don't mind communities that are overlapping, or I want to do further hierarchical clustering after you identify the communities. So various different ways of computations. So how do you detect communities? It's a computationally difficult task. Number of communities, if any, within the network is typically unknown. So this is a typical example of unsupervised learning, right? Because you don't know. You don't have a labeled graph. You don't have samples of that. So you are given a graph and say, I want to detect communities. So this is an unsupervised learning. The communities are often unequal in size and are density. You cannot assume all communities are of the same size. Size meaning number of nodes and number of edges. Oops. You can think of this as unsupervised learning. Approaches to finding communities. So one way to think of is there is this notion of cut sets. I don't know how many of you are familiar with cut sets. Cut sets minimizes edges between two partitions. So so if you minimize the edge between partitions, that means these two partitions are likely to be communities. These connections are very weak between the communities. So click-based methods, so minimum cut method is the first one, click-based method is the second one. InfoMap is a algorithm, a publicly available algorithm that's very widely used for finding communities, and we use this in our work a lot. So this exploits what is called the information theoretic duality between the problem of compressing data and the problem of detecting and extracting significant patterns or structures within those data based on information flow uses random walkers movement. So it's very difficult to explain the complete process in a short period of time, but essentially it partitions, it uses, it tries to compress and see how many different and what kind of information flow. Why information flow? Because that indicates the number of edges. Less number of edges, less information flow. More number of edges, more information flow. This is also another very popular method called the Louvain method. We use this quite a bit in our work. This uses a different way of computing communities, measures the density of links inside communities compared to links between the communities. So this is one way to think of a community. Communities are dense and the thing in between are not very dense. Networks with high modularity, so there is this notion of modularity that is defined, have dense connections between the nodes within modules, but sparse connections between nodes in different modules. Most are iterative methods. So most of these methods are iterative methods where you converge, where you keep refining what you are doing from one iteration to another iteration till there is no change. When there is no change, that means you have converged into the final solution, and that is output as the first. So how many iterations it takes, it's difficult to predict. It may take, some graphs may take more iterations, some graphs may take less iterations, depending upon the size of the graph, connectivity of the graph, and various other things. Most are approximations. They use dynamic programming because exhaustive way of doing it is almost impossible computationally. So this goes through each one of them in little bit detail. So the minimum cut method, so there are ways of, there is a partitioning algorithm called K-HIP that we use. There is also another partitioning algorithm that's very widely used. So there have been a lot of algorithms that have already been developed for partitioning graphs. The question is which one is appropriate for what you want to do and which one you want to use. So a network is divided into predetermined number of parts, usually of approximately the same size, chosen such that the number of edges between group is minimized. This can be useful in load balancing. So in parallel processing, we have the notion of load balancing. When you partition a problem and give it to different processors, it doesn't make sense if you give a very large partition to one processor and a very small partition to another processor, because the total time is the max of the times. So you want to give equal size partitions so that the time it taken in parallel will reduce and the total response time will reduce. So that is the idea. Hierarchical clustering, as we mentioned, nodes group based on a similarity measure. Cosine similarity is one, Jacquard, Hamming distance. There are a lot of different ways of measuring the similarity between nodes. Single linkage clustering that we mentioned, and complete linkage clustering. So this is used in hierarchical clustering. Betweenness, we'll come to betweenness also. This is known as the Gilman-Newman method. These are the two people who came up with this algorithm. Edges that lie between communities are identified and removed. So this is done using the notion of betweenness. So betweenness can identify what are known as bridge nodes, which means that when these bridge nodes are removed, you make the graph into two partitions or multiple partitions. So if you can identify betweenness nodes, then you can use that property to determine partitions, and then you can further try to do it within each partition till you realize that there are no bridge nodes within each partition. Click-based methods, as I said, find the maximum clicks, the clicks which are not the subgraph of any other click, consider only maximum clicks bigger than the minimum size. The union of these clicks then defines a subgraph whose components then define a community. So clicks are nothing but subgraphs in which every node is connected to every other node. Overlapping community structure, a node can be a member of more than. So Louvain method, as we said, it uses the modularity function and it maximizes the modularity. This is the optimization function. Measures the density of links inside communities. Networks with high modularity have dense connections between the nodes. Iteratively optimizes local communities until global modularity can no longer be improved given perturbations to the current community state. So all of these algorithms have a convergence. They are iterative algorithms. So most of these algorithms that are in this category, NP complete, will have a convergence condition which when reached will stop the algorithm. Same thing with the PageRank algorithm as well. Infomap, it uses a different way of approaching this problem known as the map equation. It exploits information theoretic duality between the problem of compressing data and the problem of detecting, extracting signal. So this compression is very common, is very popularly or widely used in graphs. We will see this when we do substructure discovery. We use something called the minimum description length, which is a way to compress the graph to understand whether a particular substructure is good or bad. Measures the per step average code length necessary to describe a random walker's movements on a network given a hierarchical network partition, reducing the map equation plus error. So information and Louvain of all, there are about 6 different packages that are publicly available for computing communities. I mean, you may want to look them up, and if it is of interest, you may want to play them. I mean, the best way to understand some of these things is to give a small graph. 10 nodes, 15 edges, 20 nodes, 30 edges, that you can visually understand and see, run it through the algorithm and see what it gives. It's very difficult to visualize very large graphs. I'll show you some limitations on how difficult it is to visualize large graphs, but this is how you understand and learn. Once you are convinced what it is doing on a small scale with different types of graphs with different patterns, then you know what it does. So modularity optimization that suffers from the so-called resolution limit, size of identified groups is dependent on the size of the whole network. Fails to detect clusters smaller than some scale depending upon the size of the network. So when we see that Infomap typically gives less number of communities, Louvain gives more number of communities. So Louvain gives less number of communities and Infomap gives more number. The resolution map on rather than on the total weight. As a result, the outcome of the map equation is much likely than modular maximum to be affected. So there are differences between these two. I think to summarize, this is important to understand. Different algorithms and different approaches are used for community detection. They are not based on the same algorithm, but the end goal of all of these algorithms are the same, to detect a community. And a community is somewhat loosely defined. A clique is very precisely defined. But a community is not a very precise definition. So hence, there is room for subjectivity. So you need to understand that. Hence, different algorithms are likely to give different results or different outputs for the same input graph. So this is very important to understand. You should not say, okay, I get this community in this algorithm, this community in this, which one is correct? Both are correct. But approaches are different, what they are optimizing are different. And it's very difficult. So you can test this on sample graphs. You create your own graphs where you know communities, run it on InfoMap, run it on Wing, and see what it gives. But if the graphs are very clear, if you have very well-defined clicks in every graph, both of them will give the same results. This is typically the case for these class of algorithms. So you should not start worrying about them. Then how do you deal with it? The way to deal with it is choose one algorithm and use it consistently in an application. So as long as you use the same algorithm for all the community detections in this application, you are fine. Don't mix and match. Don't use one community algorithm for one step, a different community algorithm for a different step, then you are likely to get results that are not consistent, that are not very useful. So this is what you need to keep in mind. So here are some references if you want to look up things. So any questions on community? So let us look at centrality. So what is the role of centrality node? Why is this interesting? And again, this is a graph property. You can look at it as a local graph property or a global graph property. A group of entities who share common properties play similar roles need to be treated. So this explanation is the same that we had community, but that property varies. In community, the property is connectivity, denseness. Here, it is something else. The common property is based upon degree, is based upon average shortest paths, number of shortest paths that pass through a node. So the property is different, but the general computation, what we are trying to find is the same. Several types of centrality are defined for different purposes because these have different usages in real life applications. So remember, every one of these is motivated by a real life need. It is not just defined for the sake of it. And that is important. Connecting theory to real life problem is very important. You can get immersed in theory, drown in theory, but that is of no use. I think practicality, pragmatism, connecting theory to practice is the most difficult part, but is also the most important part. So let us start with hubs. From a real world point of view, what is a hub? This one says, think of influence. What do you mean by influence? If I want to influence a large number of people, what do I choose? Who do I choose when I want to influence a large number of people? What kind of person or entity do I choose? Yes?
A celebrity.
Hmm?
A celebrity or someone who's popular.
Popular.
Yeah.
So what is popular means? What does popular mean in the graph context?
Someone that has a lot of connections.
Huh?
Someone that has connection to maximum number of other vertices.
Can you be more specific?
Like,
So a person can influence many people if he knows many people. So if you take two people, one knows 100 people, the other one knows 10 people. Which one would you choose for influencing whatever you want to, whether it's an ideology, whether it's a concept, whether you want to say something? You will use the one who knows 100 people. What is this knowing about? This is the notion of the degree. If this person is connected to 100 people as a friend, this person can influence 100 people. This person is only connected to 10 people. He can only influence 10 people. So when you think of degree, that is the number of edges incident on a node. That node can be a person, it can be a flow, other things. So nodes that have average degree greater than that, nodes that have degree greater than the average degree. Intuitively, the one that have the largest number of neighbors, or friends, or connections, or followers, that can influence best. So that is why degree centrality or hub is useful. If you want to put your money to influence a lot of people, and you want to choose 5 people, which 5 people would you choose from 1,000 people? 5 people who have the maximum number of neighbors. Right? That's how you need to think. Closeness centrality says think of information spread. If you want to spread information fast, who do you choose? For that you want to use a different criteria. You want to choose somebody who can spread information very fast to a lot of people. So based upon the average shortest path between a node and all other nodes. So if you choose the person who can connect to lots of nodes in the shortest possible way, then you can spread information very fast. Which is different from influence. So this can be used for spreading information. And why? Because the average shortest path between a node and all other nodes in the graph, that means it's like a broadcast. This person can broadcast to a lot of people with least number of hops. Whereas if you take the degree, that may have to go to a large number of hops. Smaller the value of closeness, more central is the node, and thus closer it is to all nodes. So a central node is important for information spread, not a node with high degree. Do you see that? Do you see the difference between these two? These are motivated by real world needs. Nodes having closeness values smaller than the average closeness are the centrality hubs. Betweenness. Think of control of communication. Think of control of communication or control of anything. Based on the number of shortest paths between that pass through a vertex, normalized to range, that is acts as a bridge. So if there is a bridge, think of that figure I showed you earlier. There is a river in between, there is a bridge. If you cut off the bridge, then all the communication between the two pieces are gone. Just one removal of one edge. removes all the communication. That is not true for closeness, that is not true for centrality, degree. So this is also, I mean, all of these, unfortunately, all of these used in the war situation. So when a country goes and bombs another country, they bomb centrality hubs. One disconnection can disrupt the whole thing. There is no point in bombing nodes that are already connected and does not have any effect. So this is what they do. They look for betweenness nodes, whether it's a power grid, whether it's a road network, whether it is some other kind of network, betweenness is important. If you think of spread of virus or COVID, closeness is very important. Closeness is what can spread something very fast, very quickly to large amount of people. Eigenvector centrality, think of PageRank. So eigenvector centrality is actually used in the computation of PageRank. What this says is very, very intuitively interesting. You know, you guys, I don't know how many of you write papers. Maybe you read papers, hopefully. And when you read a paper, you have a lot of references at the end, citations. So if a particular paper is cited by a lot of papers, what does it mean? That means it's a very important paper, right? Because it's an important paper, everyone is citing it. Okay? So that importance comes from the number of people who are citing it. Now that's what this one is about. Ranking of nodes based upon whether they are connected to other highly ranked nodes. But if an important paper cites other papers, these papers also become important, because this important person is citing these papers. So there is a citation network where the importance can be determined by who is citing who and why. And that property is used in PageRank, in the Chrome algorithm that you use every day. And that's what, I mean, this and additions and all that, but this is the guts of that algorithm, determining the page rank of each web page and then ranking them based upon it. So these are the 4 different ways of, so this is different from community. This is not community. So understand that. There is also one variant of this one, we will not discuss that. So some real world requirements across domain. Most influential people across different communication platforms, target of advertisement is. So you want to put money into the people who are very influential. That's why do you think film stars do a lot of advertisements? Because they're very influential. Whereas they don't pick you or me. Nobody knows us. Most dominating accident locations with respect to poor lighting, this comes from this one. Highly popular combination, highly popular preferred for various genre combinations by casting companies. So when they choose actors, they want to pair very popular actors so that total influence goes up. So compute highly central vertices, hubs in the graph. So degree centrality is the number of edges incident on a vertex. Example, number of friends a person has on Facebook. Degree based hubs is defined as the average degree greater than, intuitively, the one that has most number of neighbors. Signifies the immediate risk of a node catching whatever is flowing through the next network, such as virus and other things. Higher the degree, greater the influence. So here is an example of, so you can see in this graph, there are a lot of nodes, and you can easily see the degree of the nodes. This node has degree 2, this node has degree 2, this node has degree 2, but this one has degree 4. Similarly, this one has degree 3, so on and so forth. So in this graph, this is a hub, high degree centrality node, because the number of the rest of the nodes. So it's easy to understand. Similarly, you can see that these two nodes, or this edge, is the betweenness centrality. Why? If you look at the shortest paths between every two nodes, all the shortest paths from this side to this side go through this. So that becomes a bridge. If I remove this one, then this graph becomes two partitions. So that is the understanding of the betweenness. So betweenness essentially is the control. If I remove that edge or that bridge, two groups of people cannot interact with each other. So do you see that? Do you understand it? So here is a detailed example for this graph. How you compute it, for example, there are 6 nodes, A, B, C, D, E, F. Degree of A is 1, degree of B is 1, degree of C is 4, so on and so forth. So the average is 2. So nodes C and D and E are degree hubs. You want me to stop?
No, I just came to ask because everybody is waiting for you to meet you.
Who?
Our Rajesh Kumar Awasthi sir by chance is there today.
Okay, can I just finish this module at 2 o'clock and go home?
2 o'clock?
Yeah.
Yeah. Yeah. We can continue with this.
Yeah.
Yeah.
Okay. I continue and then come up.
No. We'll continue with this.
So you can see from here why CD is the hub. So I'm going to speed up because these guys don't want me to lecture. So let's look at betweenness. So betweenness is a little more tricky, right? You have to look at all the paths, all the shortest paths. So you can see, so for the same graph, this is the same graph. There are no paths going through A, which is short. 0, 0. But C, I am listing the paths A to B. The shortest path from A to B goes through C. The shortest from A to D goes through C. Shortest from A to F goes through C. Shortest from A to E goes through C. Shortest path. So there are 7 paths, shortest paths that go through C. There are 4 shortest paths that go through D. So C and D are betweenness hubs because their value is greater than the average. So you can take the average of this one, 7 plus 4, 11 by 6, and these two turn out to be greater than that. So, but computationally it's very difficult because you have to list all the shortest paths. Closeness centrality is different. Average shortest path between a node and all other nodes in the graph. Smaller the value, the better it is. So information spreads quickly across a network through these hubs. Think of central nodes in a graph, think of diameter radius. So here is an example of 3 things. High degree, 1, 2, 3, 4. Betweenness, you can see this is a bridge node. And this happens to be the closeness graph because this is in the center of the graph. So if you compute the shortest path from any node to all other nodes, this node will have the shortest path value. That is why, so this is not in the center of the graph. This is not, this is also not, this happens to be because there are more things on this side, less things on that side. So you can do it. Eigenvector centrality, as I said, this is used in PageRank. In neuroscience, the eigenvector centrality of a neuron in a model neural network has been found to correlate with relative firing rate, Google PageRank, etc. So here is a small toy example which indicates all the centrality. So you have degree centrality, highest, closeness centrality, betweenness centrality, eigenvalue centrality. You can check, you can play with that. So I'm going to do this in the next 5 minutes. And okay. So this is very important. We have been working on this for a very long time. We have several algorithms. We have algorithms on MapReduce. We have algorithms on partition graphs. We have algorithms on various things. A number of my master's and PhD students have done. If you're interested, just go to my website, itlab.edu. Every thesis, every master's thesis, and every PhD thesis is online. So you can take a look at it. Okay. So all the students in UT Arlington, before that I was in Florida, all the students in University of Florida, every one of them is online. All their thesis is online. All our papers are online. There are about 250 papers. When you don't get sleep, you can read one of them. You will go to sleep immediately. So one of the earliest work in graph-based data mining is subgrid. It uses a sparse adjacency matrix. It's a main memory algorithm. Substructures are evaluated using what is called a minimum description length principle I told you, which compresses a graph, capable of matching two graphs, so exactly and inexactly, performs hierarchical clustering. So this can do supervised, this can also do unsupervised, but the only problem is that this is a main memory algorithm, which means you have to load the entire graph into memory, into a data structure, and then compute it. This makes it not scalable. Not only not scalable, from our experiments, you cannot go beyond 100,000 vertices and 200,000 edges. So if you have a graph which is larger than 100,000 nodes, 200,000, the algorithm fails because, again, memory means it depends upon how much memory you have, but that's the limit we saw. A computationally constrained beam search is used, a branch and bound algorithm is used for in-exact search. So just to give you an intuitive understanding, this is what is known as the blocks problem in AI. This was very popular, this was being done for a long time. So think of this blocks arrangement, this. When you look at this, you can see that there is a rectangular block on which there is a rectangular block, and there is a triangular block, and there is a circular block. Now when you look at that, you can see that there are 1, 2, 3, 4 triangular blocks. There are 1, 2, 3, 4 rectangular blocks. There are 1, 2, 3, 4 rectangular plus triangular blocks. So the question is, so you can reduce this graph or this structure to this structure by identifying this as a common substructure. A rectangular block on which a triangle block is sitting. And then you can represent this one. So each block can be represented as a graph object. There is a triangle on this object, and there is a square on this object. And this object is on this object. So there's an object, there's a square, there's an object, there's a triangle. So you can draw this. This is a small graph. You can draw this in this. This is a graph shown in the same way to understand it better. And these are the substructures. So triangle on a square is a substructure. Square to the left of the circle is a substructure. Square on a rectangle is a substructure. Rectangle on a triangle is a substructure. So you can see different substructures within this graph. If you think of a graph that has hundreds of thousand edges and nodes, you will be able to see a lot of these substructures. So the question is, how do you identify these substructures? So for example, here is the input graph, and in this input graph you can see that this S1 repeats 4 times. So if you call it S1, then you can reduce this graph to this graph, S1, 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 and these as that. Now if you further look at this graph, you can see that this substructure S2 is the same as this substructure S2. Then you can further reduce it to S1, S2. So this is what is called compression, and the intuition is any substructure that compresses the graph very much has a meaning or value to it. So if you take a benzene structure, for example, the same pattern, substructure repeats 5 times. So because it repeats 5 times, it has a meaning in that structure. If you take some other structure, some other pattern will repeat. So repetition of patterns is very important to identify because it conveys something. It conveys a very important aspect of that application or that problem. Just like here, this conveys an important aspect that there are 4 substructures that are identical and that can be isolated. So scalable substructure, so what we did was we took this main memory algorithm and initially we put it into a DBMS. This is what I was saying, when you try to represent a graph in a DBMS, it's very awkward because it's a tabular representation. How do you represent a relationship? So we represented each edge as a row, as a tuple, source vertex and the destination vertex, source label, destination label, edge label. So you can have relations of any size. You can have millions of rows. So we did that. When we did that, we did not have to partition the graph, but we could scale up to 800,000 nodes and 1.6 million edges. Whereas in the main memory version, we could only go to 100,000 nodes. So you can see how scalability, and later I will show you tomorrow, MapReduce version. So this is a nutshell of what we did. So you can see here the sizes, 50,000 vertices, 100, 50 vertices, 100 vertices, 800,000 vertices, 1.6 million vertices. HDB subview is ours. Subview is what that stopped working. Here is that stopped working after this, and you can see that subview HDB subview goes much larger than subview. So even though the time is long, it goes to. So this is to some extent scalability. This is the crossover point, 2-point K we fault there. Subview main memory algorithm was doing better up to this point. Since then, HDB subview is being much better as well. This is how you understand what scalability is and how scalability is done. So there are other substructure discovery work. I put it, but I'm going to skip it. Just to summarize, we have graph mining, different ways of it, multiple edges, hierarchical cycles, and these are different algorithms. This is ours, this is subview. You can see that we have done a lot of things that are there. So now we are able to go to 10 million nodes and 100 plus million edges using the MapReduce scalability. So that's what I'm going to discuss tomorrow on Friday. So to summarize, graph is an indispensable data structure used for modeling large number of problems. Internet and social networks has pushed its utility. Important to understand existing work and algorithms. We have to understand a problem to see whether the analysis can be done using graph algorithms that already exist. Visualization is also important. So I'm going to stop here today. In the afternoon, I'm going to go over some case studies of analysis. So far, we have been learning concepts and theory. We'll try to apply some of these things into practical problems. Okay?
तो ऐसा बंद कर दे